Well, hello everyone. Welcome to our first Collaborate session. During this session, I'd like to talk about Chapter 5, which is about operations strategy, and Chapter 4, which is about forecasting. So let's get started. In terms of strategy, operations focuses on 4 elements or dimensions of performance. So to be competitive, companies need to have a low cost or a reasonable cost. They have to have adequate variety. They have to have really good quality, and they have to be able to deliver that product or service within a reasonable amount of time. So think about going to lunch, and let's say that there's a Subway on campus. Why do you go to a Subway? And let's just say Subway is an example of any fast food store on campus. Well, let's think about it. Typically during lunch we don't have a lot of extra time. So being able to get in and out of the store quickly is an important element to some students. Having a good variety of sandwiches and sides and toppings and even salads and pizzas, that's important to some students. Quality definitely is important to many students. Not only is the product fresh, but that we get good customer service when we're there. And then finally, the last element is cost. For fast food, we don't want to spend as much as we would for a sit-down dinner. So that's an example of a fast food store that meets those 4 elements. What about let's say you go hiking over the weekend and you trip and fall and wrench up your knee, and you have to go to the emergency room. Well, how do these elements play out for you then? Well, I think most students would say time is the most important, especially if their knee is causing them a lot of pain. They don't want to wait around forever for somebody to take a look at their injury. The next one would be quality. I mean, you want somebody who knows what they're doing to be able to look at your knee, and you want them to have the correct equipment and meds and healing outcomes that are going to help to fix your knee. The next thing is you want variety. So let's say you go to a small emergency room and they don't have a knee specialist. Well, then you might have to take an ambulance ride to a bigger hospital where they do have a knee specialist. Or let's say you go to a local hospital that doesn't have an MRI, and then you have to get transferred to another hospital for an MRI. So again, in an emergency room situation with a bad knee, variety refers to having the appropriate personnel and equipment available to adequately service your injury. Finally, cost. Maybe if we have to pay out of pocket, we're very sensitive to, but most of us have insurance, and therefore cost isn't probably on our radar as much. However, for insurance companies who have to pay the bill, cost is very important. So again, this is an example of how these 4 dimensions play out in a service setting. And these 4 dimensions, by the way, play out in the majority of profit and nonprofit organizations. So what we do in operations is we know that they're important, so we try to figure out how we can measure them. And then this is an example of just some ways that we measure cost and variety. There's 2 types of quality. First of all, product quality, or how good does the customer think the service is. And then there's a process quality versus how well the process makes or delivers the product or service compared to standards. All right, so again, in operations, once we know what's important, we try to measure it. And the other thing in operations that we recognize is that they're trade-offs. All right, so let's say like one I can think of is the variety to quality trade-off. Okay, so have you ever read about a company that tried to expand too quickly and they opened a bunch of stores or they added a bunch of products and then they kind of got too big too fast and they lost good control on their quality or infrastructure or management or whatever. And so that's a common trade-off. So you have to be very careful as you're expanding and bringing variety that you maintain good control. Another very common dimension is the cost versus time dimension. Okay, so say for example you work you work at a call center, and let's say that a fast response time to a ringing phone is important to you. Well, one of the ways that you get that is by hiring extra operators. So again, the cost of extra staff typically gives you a quicker response time. So again, there's the trade-off there. So in terms of corporate strategy or upper level strategy, we recognize that there are three generic ways that companies or organizations can gain and sustain a competitive advantage. The first one is to be the lowest cost provider of a product or service, and that's called cost leadership. The second way is to differentiate your product and service such that you can charge a little bit more for it. Maybe you sell less, but again, your revenues will be the same as somebody who is pursuing a cost leadership strategy and is just selling a whole bunch of volume at a very low cost. And then finally, there's the niche leadership. There are organizations that focus either locally on a very narrow market or a very narrow geography and are able to enhance their product or service to meet local needs. All right. And so an organization is going to decide which one of these three strategies they are going to follow. And of course, when you go and talk to many CEOs, they want all four dimensions, right? They want it all. But in operations, again, we recognize that it's very difficult to have it all. Well, you can have it all for maybe 1 microsecond, but due to the trade-offs in the organization and the dynamic nature of the industry, you won't keep it for long. All right, so here's an example of the trade-off I talked about earlier. So let's say you work at a call center, so high responsiveness is short hold times, low responsiveness is high hold times. And so if you, let's say you work for a company that wants nobody to hold. So again, you're going to follow a very high responsive strategy. You're going to hire some extra people for the phone. So again, you're going to have very low labor productivity. On the other end, let's say it's okay if people wait on the phone. So you have low responsiveness, and so therefore you don't have to hire as many operators and you can have a little higher labor productivity. All right. So so that a firm can kind of be anywhere kind of along this line. All right. And we call this line the efficient frontier. All right, so here's kind of what the line looks in our previous example. So let's say competitor A is following kind of a high responsiveness strategy. Competitor B is following more of a cost or a high labor productivity strategy. And competitor C is kind of in the middle. So let's say your company is the black dot. Now, you're not on the line. You're not on this efficient frontier. There's a gap. And so what operations does is it tries to move the bubble toward the line. It tries to eliminate the gap. And so it uses technology, it can use training, it can use different types of layouts, different ways to organize the work, etc. All right, and so this is what operations does, is it tries to make any organization as competitive as it can be based upon its strategy. All right. And so again, this is talking about redesigning processes, and that's what we do. And you get into a whole bunch of stuff when you evaluate processes and you get into designs and technology, as I said before. So it's a very dynamic and complex, but very interesting pursuit in many organizations today. And so you're probably saying, well, Dr. LeBach, that's all well and good, but does this really happen? And this is an example from the U.S. industry in 1996. And so we could probably draw the frontier like this. Maybe we could draw it like that. And so again, you can see that the majority of companies are kind of on this line. Now United, you see United over here, they have a gap, right? Delta also has a gap based upon its strategy. Southwest is doing great. It's actually moving, trying to move this efficient frontier line toward the right, which is again causing problems for all of its competition. So again, this is an example. You can see efficiency or cost is on the x-axis, and kind of yield, or this is another cost measure, I guess, yield, which would be passenger revenue per mile, is on the y-axis. So let's take a look at how this changes over time. So this is the U.S. airline industry in 2011, and you can see that the efficient frontier has changed again, all right? And so notice what we got going on here. Well, we can see Alaska, there's a gap. We can see AirTran is a gap. It looks like JetBlue and Virgin America are setting the pace and trying to pull that efficient frontier to the right and making the industry harder to compete in for the other competitors. All right, so in summary, you just can't have all four dimensions at optimum places all the time. The importance of a strategy is it's going to select or leverage what a company does well and allows it to sustain that, whatever that is, by pursuing a generic strategy. Once that is determined, then operations can come in and help maximize performance on any one of those elements based upon how far the gap is of that company to the efficient frontier. Okay, so I hope that makes sense. And anyway, that's my vision of operations strategy and why it's important and why this class is important for you all to learn. All right, so let's go on to chapter 4. So chapter 4 is all about forecasting. And forecasting is important to operations people. It's important to marketing people. It's important to accounting people. It's important to strategy people. Forecasting is the engine that drives a lot of planning and decision-making in a company. So typically you have to have some sort of forecast so you know what's coming, all right, so that you can lead the organization to that. And so we're going to look at a variety of forecasting methods, and these all are different and apply to different types of situations, and we'll talk about those as we go through. So the first thing to recognize is that some of these methods, or most of these methods are time series methods. Okay, so a time series method means what happened in the past is going to be used to predict the future. So time series forecasting relies on historical data, or sales last year, or it could be demand the year before. All right, so we have to have some historical demand to be able to predict the future, and we use a time series technique to do that. Causal methods, on the other hand, don't really rely on historical data. So as an example, let's say um, you manage a ski resort, and to be able to figure out how many ski lift tickets you're going to sell, sure, you could go look at what you sold last year, but that's probably not going to give you a really good estimate. What you probably want to look at is maybe you want to look at how much snow there is, you want to look at how full the hotels are, you want to look at consumer spending, or how much money people are spending on vacations. So all those are causal factors. They're not really time related, but they're variables that drive sales, all right, or demand. So we'll use regression as an example of a causal method. And then the last one is, typically an important meeting for many operations people is a sales and operations meeting, where, the people who sell the product or service get together with the operations people who plan to deliver the product or service, and they come on to some, agreement as to what the forecast should be. Because there could be things going on in the marketplace that the salespeople know that the operations people don't know. And again, there could be things going on within, suppliers or inventory or things like that that operations people know that the salespeople don't. And so these are qualitative factors that do get added. And again, the idea is that after this meeting, each group leaves with some common understanding of what the forecast will be. All right, so some assumptions. First of all, the majority of the methods that we are going to use are time series methods. The only method that isn't like that is regression, as I said. So for the most part, we're going to assume that the same underlying factors that existed in the past will exist in the future. So we're not going to be dealing with any new product rollouts, any products that, for instance, I'm just trying to think of like an example. Let's say that there's what is the name of that ice cream? I'm trying to think of that had salmonella in it, and Bluebell ice cream. And so it's got all this, demand for it is dropping and all this other stuff is happening. We're not going to assume any of that. We're going to just assume a very constant, stable demand profile. The second thing to recognize is that all forecasts have error. You will never get a technique that will be perfectly accurate. And so what we do in operations to manage the error is that we group similar items together and forecast them in aggregate. So as an example, if a company has 5 different cell phone models, we would aggregate those 5 models together and then do one forecast for all 5, and then after the forecast, disaggregate it. And the reason we do that is because errors can kind of cancel out each other. And so if you do them in aggregate, you'll get a more accurate forecast. And again, if you're forecasting farther out in the time horizon, you're going to have more error than if you're forecasting closer. So if I have a 5-year forecast, that's going to be less accurate than an 18-month forecast. And then there's other elements that are important other than accuracy when you're talking about forecast methods. You need to get an answer quickly. They need to be, again, accurate, but forecasts should be consistent. You don't want one bouncing all over the place. Should be easy to use and be cost effective. So all those other factors are important as well. Okay, so I talked a little bit about accuracy, and we're going to measure accuracy to make sure our forecasts are accurate. And we're going to measure accuracy by measuring error. And we're going to measure it in the following 4 ways. So the first way we're going to measure error is with bias. All right. So number 1 says bias. So the bias in any period is the actual demand minus the forecast. So the error is going to be what we thought we would get what we actually got minus what we thought we would get. All right. And so again, if your bias is positive, this means that you're under forecasting, right? And if your bias is negative, it means that you're over forecasting. All right, so again, we want the bias to be as close to zero as possible. But again, it's never going to be exactly zero, but we can look at the sign on it to know how we can adjust our forecast to make it more accurate. The second one is called the MAD, or the mean absolute deviation. And again, you see these little football goalposts here. This means the absolute value. So we're just going to take the absolute value of the bias. And so we don't allow any negative numbers. So again, it's kind of like playing horseshoes. We don't care if it's to the left of the horseshoe pin or the right of the horseshoe pin. We just care about how far away it is from the horseshoe pin. And so we take the absolute value of it. And again, the absolute value, or the mean absolute deviation, just tells us, again, how far away we were. And we don't care if we were under or over. The third one is more of a statistical concept. It's called the mean squared error. And again, if anybody remembers statistics, all it is it's the MAD squared divided by n-1. So it's a sample variance is all it is. All right. And then the last one is used when you're forecasting really large numbers. So maybe we don't really care how many units away we were with our error. We care more about what percent error we have. So, you know, if you're looking at forecasting airline miles, I mean, you can get into the millions and billions of airline miles. And let's say you get an error of 1 million. That's quite a lot. But if you do the percent error, it might show that it's only 1%. So this mean absolute percent error is just the MAD divided by the actual demand. And it gives you a percent error versus an error in terms of units. Okay, so we're going to use these four measures for accuracy. All right, so let's look at an example here. And I'm going to use the same numbers with all examples or all different types of forecasting techniques that I do. All right, so this is our demand. You can see in period 1, we have 21. In period 2, we have 23, etc. Now, the first technique that we're going to look at is called naive. And naive it's again a time series method. Very easy to use. And so a lot of like mom and pop shops use this. You don't need a computer. What it says is that so let me type this. So the naive method says that the next period's demand, what happened there? The next period's demand is equal to the previous period's demand. Okay? So in other words, let's see what I did here. So in other words, let me draw this here. So at the end of period 1, we're wondering what the forecast is for period 2. Well, the forecast for period 2 is just the actual demand from period 1. The forecast for period 3 is just the actual demand from period 2. Okay, etc. And you just go through and you shift the actual period's demand down by 1 period for the forecast. Okay, that's all you do. So now you can see, let's look at period 2. You can see period 2 has an actual demand now of 23, and it has a forecast of 21. So this is the bias. Remember, the bias is the actual minus the forecast. So 23 minus 21 is 2. The MAD is the absolute value of the bias. So again, it's 2. The MSE is going to be 2 squared divided by 1, which is 4. And then this MAPE is going to be 2. So it's going to be 2 divided by your actual demand of 23. All right. So it's going to give you 8.7%. So what we're going to do is we're going to do that for each row. And then down here, what we can do is we can get an average. All right. So if I add up all these biases, so let's see, some of these cancel out. So we get 7, 11. So we get 5 over 1, 2, 3, 4, 5, 6, 7, 8. We get 5 over 8 periods, which is 0.6. So that bias of 0.6, again, it says that it's positive. It's pretty close to 0, which is good. But because it's positive means that we're slightly under forecasting. Let's look at the MAD. So again, if you add all the MADs up, so this is 2, 4, 5, 6, 8, 17, 21. So we get 27 over 8, which is 3.4. So again, the goal with all these accuracy measures is we want them to be as close to 0 as possible. So 3.4 means that we're off by 3.4 units, either under or over. So what this means to us is we either have to have 3.4 units of safety stock, or we're going to have 3.4 units of extra inventory somewhere that we have to pay for. So again, we're just going to be off. The 3.4 units is the cost of doing business and the cost of the error to us. MSC, again, it's 21. I'm not going to add all those up, but it's just add them all up, divide by 8. And the average MAPE is about 13%. So it says that our error is about 13% of our average actual demand. All right, so again, what we're going to do to determine the best method is we're going to see which method gives us the lowest averages in each of these 4 error metrics. So this one, again, the bias on this one looks pretty good. It's pretty close to 0. The MAD looks okay. 3.4 is not, all that great. And again, the MSC and MAPE, not fabulous, but again, the other techniques could even be worse. So again, what we're going to do is mark down these averages for the naive method, and again, see if we can find a better technique. Now, this next graph shows this kind of like pukey yellow line. It looks like baby food, actually. I feel sorry for babies, but anyway, it's you can see what the actual demand, and then the forecast is a mirror image of that, but just offset by 1 period. And so here you can see this is where we get all that error. We're very slow to react to that jump that occurs in period 8. There's a little bit error over here too, but certainly not as much as in this bigger chunk. Okay, so moving on. Let's take a look at moving averages. So what moving averages do, and in this case, it's a 3-period moving average. We're going to take, again, this is the same demand as what we had before. So what we're going to do is we're going to take the most recent 3 periods, so periods 1 through 3, and we're going to average them and use that average for the forecast for period 4. So again, we wait until we're at the end of period 3, so we know we have actual demand for period 1, 2, and 3. We average all of those and use them for the next period's forecast. And then, so for period 5, again, we're going to take periods 2 through 4, and we're going to average them and make it for period 5. And then keeping going with that, so periods 7 through 9, we'll average those, and again, use those for period 10 forecast. So again, a moving average of 1 is the naive method. You can have moving averages from anywhere from 1 to however many periods that you want. Again, the more periods that you use, the more of a smoothing method you're going to get. All right, and I'll talk about that in a minute. So again, let's take a look at period 4 here. We have a forecast of 21.7. So the bias is going to be the actual minus the 21.7 or minus 1.7. The MAD is going to be the positive of that, or positive 1.7. The MSE is going to be 1.7 squared over 1. And the MAPE is going to be the 1.7 divided by 20, or 8.3. So again, we're going to average all of those over, it looks like over 6 periods, not 8. And we can see that the bias is a little higher than it was with our naive method, 2.2 versus 0.6. It's still positive, which means we're under forecasting. We can see that the MAD is also slightly higher. We had 3.4 in our naive method, and this shows a 3.6, so it's a little higher. The MSE and the MAPEs, those are also, well, the MAPE is a little lower, but the MSE is a little larger. So this technique gives us some different results. And again, you can see this green line. Do you see how slow it is to react to that bump? This is the smoothing. It just smooths out that blip. It doesn't immediately react to it. And so this gets into making consistent forecasts. I mean, if you're trying to forecast something that looks like this, I mean, maybe you want, let me do this in a different color. Maybe you want a forecast to look like this. You know, you don't want it really nervous and bumpy like that, because believe me, operations people hate all that variation. It'll make their jobs a lot harder, and again, it'll just drive them crazy. So, and I think a straighter line in this case would be more accurate, because you're going to cancel out errors there. Okay, so let's move on. The weighted moving average. Okay, so let's go back. Let me just explain something here. So with a moving average, so let's say we have a moving average. It gives, let's say we have a 3 moving average. It gives each previous or historical data 1/3 weight. So if you have a 3-period moving average, each of those 3 periods gets 1/3 weight. What we might want to do, and what this technique does, is we might want to give more weight to the newer data, all right? Or sometimes if we do it like T-1, T-2, so it looks something like this. Okay, so you could see, so this is the oldest data here, the weight on that. This is the newest data here. So now instead of a straight line, we have kind of like a linear curve going straight down. Oops. And there we go, just linear curve straight down. All right, so again, for a weighted moving average, it works the same way, but you're going to give the biggest weight to the newer data. And the other thing to keep in mind is your weights have to add to 0, or to 1, I'm sorry. So what we're going to do is we're going to give the period 4 demand the weight of 0.4. We're going to give the period 3 demand the weight of 0.3. Period 2 demand of 0.2, and period 1 demand of 0.1. So this 21 here is going to be equal to the 0.4 times 20 plus 0.3 times 21 plus 0.2 times 3 plus 0.1 times 21. All right? So you can see instead of giving each one a 25% weight, like we would in a 4-period moving average, we're giving the newer data more weight, okay? And so you're just going to continue down like that. So to get this 20.9, all right, we're going to take, again, the previous 4 data. And in this case, we're going to give the 21 the 0.4, the 20 the 0.3, the 21 the 0.2, etc. All right. And so again, we come down here and we can get our averages on our bias, MAD, MSE, and MAPE. And you can see that these are a little higher than what we've had so far. And if you look at the graph of it, you can see all this is error. Okay, so this technique seems to have increased the amount of error. And again, it's not as accurate as the other two. Okay, exponential smoothing. Now, what I was saying before we go into these examples, I hope you can see them. Remember what we were saying here about like a regular moving average has equal weight to all historical data. And then we tried weighted moving average, which now has this downward linear slope. What exponential smoothing does is it actually tries to do this exponential smoothing profile. Here, hold on, it's blue. I don't know if it shows up blue to you, but it's showing up blue to me. And it's going to look like this. Okay, it's going to, instead of being a straight line, the weights, it's going to give an exponentially bigger weight to the newer data, and it's going to give a decreasingly exponential weight to the older data. So the formula that we're going to use for exponential smoothing is this one. All right, so the forecast for any period t is going to be alpha. So alpha is what's called a smoothing constant. And alpha ranges from 0 to 1. All right, so the alpha is going to tell you how much weight you're going to put on the previous actual demand. If alpha is 1, you have a naive method. So typically alpha is low. It's in the 0.2 to the 0.4 range. We typically don't want to put a lot of weight on alpha because, again, that's just going to, it's going to change this exponential curve to something that looks more like a linear line. All right, so let's just do an example here. So here's our data. So in period 1, we had 21. Now with exponential smoothing, the other thing is we have to prime the pump. Okay, what do I mean by that? To get this model going, we have to assume F1, or F in this case, F minus 1, all right? So we're going to assume F1 is equal to A1. So we're going to assume that the initial forecast for period 1, F1 here, is the same as A1, all right? So 21 equals 21 there. Now when we get to period 2, we have F2, and let's say, what do I have here? Alpha is what, 0.2? Is that what I have here? Yeah. So F2 is going to be alpha, which is 0.2, times the actual demand, which is what, 23? Plus 1 minus alpha, which is 0.8, times F1. Well, we just said F1 was equal to A1, which was 21. So this is going to tell us F2 is going to be what, 21? Let me just see, what is that? Can't read it now. F2 is going to be, what is that, 21? 21 point something, I can't read it. My bad. Okay. But anyway, that's how you use the formula. So then again, F3, and I wish I could make this bigger. I'm so sorry. Okay, so again, F3 is going to be alpha times A3, which is 21 again, plus 1 minus alpha, which is 0.8 times whatever we got for F2. And then you can see that F3 is 21.4. Okay, so once you get all of these forecasts done, then you can do all the accuracy measures. And again, you can see that the averages are down here. And this is alpha 0.2 up here. And this is alpha 0.5 down here. So what I've done is I've changed the alpha to get the best forecast. So how do we do this in real life? Is we just randomly pick some alphas and we keep trying different ones until we get the best forecast. All right, so that's where the alphas come from. So again, you can see the higher alpha gives you a little more reactiveness here because you're putting more weight on the previous actual demand. So in this case, we see that a higher alpha gives us a little less error than the lower alpha does. Okay, because this lower alpha, what it wants to do is just wants to smooth all this out. The higher alpha is going to react a little bit more to every little bump and grind there. All right. So we've looked at a whole bunch of time series models that we can use to forecast. Now let's look at a causal model. But to do this causal model, I'm going to cheat a little bit and use time as a variable, okay? So your book has a pretty good method for figuring out what the regression equation is. And the other thing you can do is you can use Excel, or you can use like some statistical programs. You're going to put in, so again, you're going to put in X and Y data. And so we already know that this is what our XY data looks like. So X is time, okay, and Y is demand. And so what regression does is it's going to try to fit a straight line through all these data points, okay? It's going to square at certain points. It's going to square the distance between the line and the actual data and add them all up. And that's going to be the sum of the error, sum of the squared errors. And then it's going to pick the line that gives you the least sum of squared error. And this is called the sum of the squares method. All right, so this regression line equation here defines the line that goes through this data. So what it says is it says 18.4, well, that's the y-intercept. So we know at time 0, we have 18.4 units. And it says here that we have a slope of 1. So every period, we're going to grow that demand by 1. All right. So whatever method you use, you can either use the one in the book, you can use a calculator, you can use Excel. But the important point here is to get this equation. And once you have this equation, you can forecast. All right. So for example, if we could look at the next slide. Oh, for some reason, I don't have another slide here. Okay. So what we would do here is we'd have so here's period 1. Our actual demand was 21. The forecast would be 18.4 plus 1 times period 1. So the forecast here would be 19.4 for period 1. For period 2, our actual is 23. And again, our forecast is going to be 18.4 plus 1 times 2, or 20.4. Okay? So that's how regression works. And since we ran out of slides, I'm going to let you guys get started with this, and then I'm going to see if I can load the slides up tomorrow, and we'll talk about the last technique, which is the trend-enhanced exponential smoothing model. All right, but this should at least get you started on the homework. And again, if you have any questions, let me know. Have a good night, everyone. Bye now.